Welcome to the deep dive. Today we're jumping into something with really significant potential. How AI is changing the way we analyze medical images.
It really is a huge area.
Yeah, think about, AI quickly scanning chest x-rays for pneumonia, maybe COVID-19, even tiny lung nodules.
Or identifying brain tumors, looking at knee disease risk factors from x-rays. It's about potentially catching things earlier, more accurately.
Exactly. Not just faster, but maybe even better in some ways.
Well, that's the goal. And deep learning, especially convolutional neural networks or CNNs, are really central to this. Their power lies in automatically learning crucial visual features from these, complex images. It can speed things up massively and give doctors a sort of second set of eyes.
Okay, so let's unpack that. Instead of a radiologist looking at every single detail, the AI learns patterns. Maybe even patterns humans miss.
That's the idea. But like anything trying to understand the human body, it's not straightforward. There are definitely challenges.
I bet. What kind of challenges?
A major one is imbalanced data sets. In medicine, some conditions are just way more common than others.
Right. So the AI sees loads of normal scans, maybe, but very few of a rare disease.
Precisely. So it gets really good at spotting the common stuff, but struggles with the rare, potentially critical cases. It's like finding one specific needle in a giant haystack.
Yeah, that makes sense. The lack of data skews the learning. What else?
Then there's the problem of overlapping classes.
What do you mean by that?
Well, sometimes the visual differences between, say, two types of tumors or different stages of a disease are incredibly subtle, almost indistinguishable to the naked eye sometimes.
Like telling apart two very similar shades of gray.
Exactly. If the AI can't learn those fine boundaries between conditions that look alike, you get misclassifications, errors.
Which is obviously not good in a medical context.
Definitely not. And this brings us perfectly to the focus of our deep dive today, a new CNN training method called CLOG-CD.
CLOG-CD. Okay, intriguing name. What's the core idea? How does it tackle these data issues?
So, CLOG-CD stands for Curriculum Learning based on oscillating granularity of class decomposed. It's basically a clever way to train these CNNs by combining two concepts, curriculum learning and class decomposition.
Curriculum learning.
Right.
The school curriculum and class decomposition. Breaking things down.
You got it. Curriculum learning is about ordering the learning, simple to complex. Class decomposition breaks down tricky classification tasks into easier subtasks. CLOG-CD merges these.
Okay. So our mission today is to figure out how CLOG-CD works and why it seems to be getting better results on these tricky medical data sets.
Exactly. Let's get into it.
Right. Let's start with curriculum learning. That name implies like a lesson plan for the AI, right?
Precisely. The basic idea is borrowed straight from how we humans learn. You start with the easy stuff, the basics, and then you gradually move to more complex things.
Like learning scales on a piano before trying a concerto.
Perfect analogy. So you don't just throw the most complex medical images at the AI right away. You start simpler.
Are there different ways to structure that? Like always easy to hard?
Well, that's the traditional approach, yes. Easy to hard examples. But interestingly, there's also something called anti-curriculum learning.
Anti-curriculum. So hard to easy.
Yeah, starting with the tougher examples first. It sounds a bit counterintuitive, maybe.
It does. So what makes either approach work? What are the key bits?
Two main things. First, the scoring function, which is basically the training scheduler. It defines what's easy and what's hard and plans how it introduces them.
Okay, defining the difficulty.
And second, the pacing or speed functions. These control how fast you ramp up the complexity for the AI model.
Got it. Difficulty definition and the speed of increase. Now the other piece, class decomposition. What's that about?
Class decomposition, you can think of it as a kind of divide and conquer approach for supervised learning, for classification tasks.
Divide and conquer, breaking a big problem into smaller ones.
Exactly. Especially useful when you have multiple classes, and particularly when those classes are imbalanced, like we discussed.
The rare disease problem again.
Right. The idea is to improve how the model learns the boundaries between the original classes by first clustering them into smaller, sort of more focused subclasses. This happens before the main training starts.
So instead of distinguishing 5 types of knee arthritis at once, maybe you group them first. By severity, perhaps?
Something like that, yeah. You create these finer subclasses, making the initial job simpler for the model. But, and this is important, the performance really depends on the granularity of this decomposition.
Granularity, like how fine you chop it up, how many subclasses you make.
Precisely. You can't just dice it up randomly. There's a sweet spot for how detailed that initial breakdown is.
Okay, that makes sense. So now the big question, how does CLOG-CD actually combine curriculum learning with this class decomposition? That's the novel part, right?
Absolutely. This is where CLOG-CD gets clever. It integrates the two, but the key innovation is using the granularity of the class decomposition to actually guide the curriculum learning.
Whoa, okay. So the level of detail in the breakdown sets the learning path. How does that work?
They use something called oscillating granularity. So it might start training the model with a high level of granularity.
Meaning lots of very specific subclasses.
Yes. And distinguishing between these many fine subclasses can actually be easier initially because the differences, the boundaries, might be clearer.
Okay.
Then the training moves to lower granularity levels, fewer, broader subclasses, which might be harder to tell apart.
And oscillating means it goes back and forth.
Exactly. It might cycle between high and low granularity levels during training.
Huh. Oscillating. Like focusing a camera lens, maybe. In and out. Why do that? Why not just go from, say, high to low and stop?
Good question. The thinking is, starting high lets the model easily pick up basic, important features for those very specific subclasses. Then, moving lower forces it to learn the more subtle features needed to distinguish the original, broader classes.
And oscillating reinforces this.
Right. It lets the model revisit and refine features learned at different detail levels. This whole process is thought to make the learned features more transferable, more robust, improving how the model generalizes to new images it hasn't seen.
So varying the difficulty stops it getting stuck on just one level of detail and helps it build a more complete picture.
That's the idea. It forces a more robust kind of learning.
It feels like learning brushstrokes, then the whole painting, then back to details. That actually sounds quite logical for complex images like scans.
Okay, can we get into the nitty-gritty? How does CLOG-CD actually do this, step by step?
Sure. So first step is the class decomposition itself. For this, they use a convolutional autoencoder, a CAE.
Autoencoder, that compresses data, right?
Yeah, think of it as a way to automatically learn the really important visual bits in the images. It has two parts. An encoder that compresses the image into a compact numerical summary, the latent space vector.
Capturing the essence. Right. And then a decoder tries to rebuild the original image just from that summary. To do that well, the encoder has to capture the crucial features.
Okay, so the CAE extracts the key features. What happens to that compressed summary, the latent vector?
That vector, holding the key features, is then used to split each original medical class into subclasses at different granularity levels. They use the k-means algorithm to do this clustering.
K-means grouping similar things together.
Exactly. And in their work, they used K5. So for each original class, k-means finds 5 subgroups based on those CAE features.
So if K was 4, just as an example, each original class gets split into 4 subclasses.
Yep. They denote that level as G4, and they create different levels. G5, 5 subclasses, G4, G3, G2, and then G1, which is just the original dataset, no decomposition. So the whole sequence goes from most granular G5 down to the original G1, G5, G4, G3, G2, G1.
And each little subclass gets its own temporary label, like pneumonia type A.
Exactly right. A new label, but it keeps track of the original class. These subclasses are treated as distinct categories during this phase. But then, after training, they're recombined for the final classification.
Okay, so you break it down, train on the pieces, then put it back together. Makes sense. Now, the oscillating granularity mechanism, how does that work in training?
Well, remember the scoring function from curriculum learning, defining easy versus hard.
Yeah.
In CLOG-CD, that's implicitly set by the granularity level. Higher granularity, more subclasses, is considered easier.
Because the boundaries are clearer between those finer groups.
Precisely. Easier to distinguish visually. And yes, they still use standard stuff like mini batches and stochastic gradient descent, SGD, to train the main CNN.
Okay, standard training tools.
Now, the pacing function decides which samples within a batch are used at a given granularity. And the oscillation step, they use the symbol delta, that defines how big a jump you make between granularity levels. They tested steps of 1, 2, and 4.
So IR1 means moving one level at a time. G5 to G4, G4 to G3?
It's exactly. Sequentially. Then there's the training direction, beta. Beta means purely descending granularity.
G5 down to G1. Starting granular, getting broader, like that anti-curriculum idea.
Right. They call that CLOG-CD, DEG, for descending granularity.
And beta 1.
Beta 1 involves both ascending and descending. They also tested purely ascending, G1 up to G5, which they called CLOG-CD ASG. That's more like traditional CL.
ASG for ascending. DEG for descending.
But the full oscillation, beta 1, means going down and back up, or maybe up and then down, maybe repeating the cycle. So with R1, it could be G5, G4, G3, G2, G1, then back up, G2, G3, G4, G5. And they repeated that whole cycle, like 20 times for one network.
Wow, okay. That's a really specific dance through the difficulty levels. And they tried bigger jumps too, UR2 and UR4.
Yes. UR2 would be bigger steps, like G5 to G3 to G1, then maybe back up G3 to G5, and UR4 is even bigger jumps, G5 straight to G1, then back to G5. They wanted to see which oscillation pattern worked best.
Fascinating. So after all that complex training choreography, how did they measure if it actually worked better? What metrics?
Standard metrics for this kind of task: accuracy, precision, recall, and the F1 score, which balances precision and recall.
Okay, the usual suspects for classification.
And crucially, they calculated 95% confidence intervals over multiple runs. That gives you a sense of how reliable the results are.
Right, consistency matters.
Right.
Okay, let's get to the proof. The data sets. What real-world medical images did they test this on?
They used 4 different data sets, all known to be imbalanced. Chest x-rays, CXR, with 4 classes.
Pneumonia, COVID, nodules, normal maybe?
Something like that, yeah. Then a brain tumor data set with 3 types, a digital knee x-ray set with 5 classes, likely osteoarthritis grades, and a histopathology colorectal cancer, CRC, data set with 9 tissue types.
A good mix, different body parts, different image types, different numbers of classes.
Exactly. Provides a solid test. And they used pre-trained networks as the base, which is pretty common.
Saves time and leverages existing knowledge, right? Which ones?
ResNet-50, a 50-layer network, and DenseNet-121, which is deeper, 121 layers. They fine-tuned these using a deep tuning strategy on their medical data sets.
Okay, and standardize the images.
Yep, all resized to 224 by 224 pixels. Standard practice. They also did a standard data split. 70% for training, 20% validation, 10% for the final test.
And they detailed the whole setup, hardware, software, learning rates, all that.
Oh yeah, very thoroughly. Which is great for reproducibility. Specifics on batch size, epochs, optimizer settings, regularization, everything.
Good science. Okay, the moment of truth. What happened with ResNet-50? How did CLOG-CD do?
So the results were pretty clear. Across all 4 data sets, the CLOG-CD version using that oscillation step of U1.
The one moving between adjacent levels.
That one consistently got the highest accuracy. It beat the baseline ResNet-50 trained normally, and it also beat the other CLOG-CD variations, the purely ascending ASG, purely descending DEG, and the bigger oscillation steps, O, U4.
Wow, consistently. Even without extra tricks like data augmentation.
Yes, the improvement was there both with and without data augmentation, which really highlights the strength of the CLOG-CD method itself. The jump in accuracy was often quite significant.
That sounds really promising, especially for those tricky imbalanced data sets. Can you give us some numbers, like how big were the improvements?
Sure. Let's take ResNet-50 with augmentation. For the chest x-ray set, baseline was about 91.7% accuracy. CLOG-CD pushed that to 96.1%.
That's a solid jump.
For brain tumors, it went from about 90.9% baseline to 96.9% with CLOG-CD.
Yeah.
Even bigger improvement there.
Wow.
The knee x-ray data set saw a huge leap from around 63.7% baseline accuracy up to nearly 79.8%.
Okay, that's substantial.
And for the colorectal cancer data set, already quite high baseline at 97.3%, CLOG-CD do-free still boosted it to 99.2%.
Impressive. So that UR1 oscillation seems key. Did the same pattern hold when they used the other network, DenseNet-121?
Largely, yes. The trends were very similar with DenseNet-121. Again, CLOG-CD with UR1 generally came out on top compared to the DenseNet baseline and the other CLOG-CD types.
Same winning strategy.
Pretty much. The specific numbers changed slightly, of course. For DenseNet-121 with augmentation, CLOG-CD hit, 94.9% on chest x-ray, 94.6% on brain tumor, 76.2% on knee x-ray, and a really high 99.5% on colorectal cancer.
So the benefit seems robust, works with different network backbones. Did they compare it to other types of curriculum learning methods?
They did. They tested it against a couple of others, like DCLU and one based on prior uncertainty. And CLOG-CD generally performed better or very competitively, especially on the chest and knee data sets in their comparison without augmentation.
Okay, hold its own against related techniques. What about against, just any state-of-the-art method people have tried on these specific data sets before, even non-CL ones?
Yeah, they looked at that too. And CLOG-CD's results were right up there, often exceeding published state-of-the-art accuracies for these data sets achieved by various other advanced methods.
So competitive or even better than the best results previously reported in many cases.
Exactly. For instance, that 96.1% on chest x-ray with ResNet was better than several other top methods cited. Same story across the other datasets. CLOG-CD was consistently performing at or near the very top.
Okay, so let's try and wrap this up. This CLOG-CD approach, mixing curriculum learning and class decomposition with this oscillating granularity idea. It really seems like a significant step for handling these messy, imbalanced medical image datasets.
That sums it up well. Its real value is that unique integration, tailored for the kind of data irregularities you see all the time in medical imaging.
And the big takeaway feels like this. CLOG-CD, especially that OCA1 oscillating version, just worked better. Consistently better across different diseases, different data sets, different AI architectures, compared to standard ways of doing things and even other curriculum learning ideas.
Precisely. It really highlights the benefit of starting simpler. With those decomposed classes, letting the model grasp basic features first before tackling the harder original class boundaries.
And the oscillation gives it an extra edge somehow.
It seems so. That back-and-forth refinement appears to really boost the final performance.
Okay, my aha moment here is realizing that sometimes learning the simplified, broken down version of a problem first, and even going back and forth between levels of simplicity can actually lead to a much better, more robust understanding of the original complex thing.
That's a great way to put it. It's not just about difficulty, but about building understanding layer by layer, revisiting foundations.
It's like you need the simple scales before the complex music.
Exactly.
So for you listening, maybe the final thought is this. Could this idea, curriculum learning guided by decomposition, work elsewhere? Outside of medicine, think about other fields with complex, maybe imbalanced data. Finance, climate science. How else could you define simple versus complex to guide AI learning in those areas?
That's a really interesting question. The core principles start simple, progressively increase complexity based on some meaningful decomposition they feel quite fundamental. It definitely suggests broader potential and opens up exciting avenues for future work, a very compelling direction.